In the previous lectures, I have explained formation of inversion layer for N-type enhancement type MOSFET. Referring to this energy level diagram, when we apply negative gate bias, intrinsic energy level shifts downwards. And this energy QVF is very important in this explanation. This indicates the strength of doping of P substrate material. Higher the value, it's called highly doped. Lower is the value, then P-type substrate is supposed to be lightly doped. The moment EI level goes down at this point, when it is lowering down, the gap between EI and EFS at this point near the interface decreases. That indicates P-type substrate near the interface becomes less P-type, lightly doped. At some point, when EI becomes EFS at this point, center point, P-type substrate near the interface becomes neutral, intrinsic, where N is equal to P. After that, when EI goes down below EFS, the inversion of P-type substrate starts. That means the nature of P-type substrate near the interface starts changing from P-type to N-type. This is called inversion layer. At some point, when EI is equal to EFS, in that case, P-type substrate becomes intrinsic, where N is equal to P. After that, when EI goes down and it shifts down below Fermi level energy for semiconductor, then the inversion starts. That means P-type substrate starts changing from P-type nature to N-type nature. This is called inversion. And from the last lectures, we understood one thing. For strong inversion, this energy should be equal to double of this energy. That means QVS must be equal to 2 times QVF. And for strong inversion, EI should shift down below EFS as far as below as it was above for P-type. And this is the case for strong inversion. In this lecture, I will explain concentration of electrons and holes near the interface. Then I will derive the expression for electric field across the interface and also derive the expression for surface charge per unit area at insulator-semiconductor interface near this zone. Because in the bulk of P substrate, that remains neutral. And before explaining the concentration, I define one more quantity. This is called this energy QV. V is the potential near the interface. Vs is the surface potential. When Vs is 0, that means flat band condition. V is general condition and general voltage near the interface where there is a gap. You see one thing, at this point, this is the part which remains when it goes down. This is lower value. That means here concentration and doping of P substrate reduces. We have to calculate the concentration by using different standard equations like this one. This is N naught. This is the equilibrium condition for concentration of electrons. This N naught and P naught are for this region away from the interface. This region. For this region, concentration of electron can be described by this equation. And there is a gap, EI minus EFS. This gap is equal to QVF. There is a minus sign. Minus sign is because of we are discussing for electrons. And this is the expression. Now, near the interface where V comes, I am calculating the concentration of electron near the interface in terms of V by putting the value where Vf is equal to now Vf minus V. Now, this is the expression. This is the expression for concentration of electron near the interface. Similarly, we will calculate concentration of holes in bulk of the semiconductor here. This is the concentration, EI minus EFS as a standard value. Then again, this difference is equal to QVF. Now, concentration of holes near the interface or in the inversion range can be calculated by putting value in terms of V. So Vf is now replaced by Vf minus V. Now we get this expression. This expression. From these four expressions, 1, 2, 3, 4, we see very important situation here. In this range, N naught is less than P naught because this is of P type nature. That's why this must be greater than this one. And the inversion range, the matter is reverse. This is greater than this. Mathematically, we can see here, this is a concentration here, and this is a concentration here. But this is for electron and this is for holes. You see, there is a negative sign and there is a positive sign here. Negative sign means it's a lower quantity, lower magnitude, and positive means higher. That means P naught is greater than N naught here. Now, in the inversion range, this is for inversion range, this one and this one. Here, N is plus QV and P is minus QV. This is higher, this is lower level. That's why N is greater than P in the inversion range. So this is all about equation for concentration of electrons and holes, and there are two zones. This is neutral zone and this is inversion zone. So 1, 2, 3, 4 equation. These equations are very important. In the next part, we will be using these equations to find out the expression for the electric field and surface charge per unit area at insulator-semiconductor interface for NMOSFET. I am considering the standard model for NMOSFET. Free electrons obey Fermi-Dirac distribution, and for potential variation in semiconductor, we are using Poisson equation. This is the Poisson equation and this is the potential difference, double derivative with respect to distance. And this is the charge density at point X. This is equal to Q. This is concentration of P, concentration of electrons and concentration of immobile acceptor ions, where Na is equal to P naught minus P naught. One point is to be noted here. In this expression, we don't have this term Nd. This is the concentration of immobile donor ions. Basically, in MOS structure, we don't have N-type substrate. That's a different thing. We have induced one inversion channel that is made of only electrons, and there is no need of concentration of donor ions. Now, we know the values of P and P naught and naught from the last page, and substituting all the values in this equation, you find this is the extended form of Poisson equation, integrating with the proper limit, and this is the result of the integration. And this thing, this quantity is nothing but the electric field over here, and this is the expression. And taking a square root, this is the expression for electric field at the interface. And at interface, electric field may be written as ES and surface potential may be written as VS. I am defining one more term that's called Debye length. This is equal to LdP and this is equivalent to this. We'll put this, this and this in this equation. Debye length is the length over which charge carrier screen electric field. This is the expression for electric field at the interface in terms of surface potential. And as per Gauss Law of electrostatics, this is the law of electrostatics, Gauss Law, we can find Qs, that is the surface charge per unit area or surface charge density at the interface. We are using the modulus because charge is negative. This is the expression for surface charge per unit area in terms of surface potential, and dependence of surface charge per unit area on surface potential is shown in the following graph. I will explain, and that will indicate transition from accumulation to flat band to depletion to weak inversion and finally to strong inversion of conducting channel in NMOSFET. Considering NMOSFET And this is the expression for charge per unit area at the interface for different values of surface potential. Referring this graphical representation where modulus Qs is shown on y-axis and surface potential is shown on x-axis. And this is the 0 for x-axis. Here this is the direction for negative value and this is for positive values. And this Vf can be defined this way. This Q times Vf is equal to EI minus EFS. This is the gap between intrinsic level and Fermi level for p-type substrate. These three levels are also shown: EV, EI and EC. These are for p substrate. This is for valence, intrinsic and conduction level of energy. Now there are 5 different bands for this graph depending upon the value of surface potential. The very first one is when surface potential is negative, when it is 0, when its value is between 0 and Vf, when its value is more than Vf but less than 2 Vf. And the fifth one is where surface potential is more than 2 Vf. Let us consider the very first zone, this one where potential, surface potential is negative. Just refer this equation, and this Q is positive, V is minus. That means this term, exponential term, is dominating in this expression. And this is negative quantity, that's why this term is dominating. We can say Qs is increasing exponentially for higher negative values of surface potential. And this is here. This way, negative value is increasing for surface potential, and this is a rise, exponential rise in Qs. And this is the zone, this is the reason it is known for accumulation of holes. This is the case when we apply a negative potential at the gate. It start attracting holes from the p substrate towards interface where population of holes start increasing, and this is the concentration of hole is greater than the concentration of immobile acceptor ions over here. For the second zone, this is where surface potential is 0, and this is the condition for flat band where EV, EI, EC, all levels are flat and parallel, and there is no bending upward or downward, no bending or shifting is there. For the third reason, where surface potential is more than 0 but less than Vf, this is the reason known as depletion reason. In this reason, because of positive potential at the gate, that start repelling holes away from the interface. That's why the population of holes near interface start decreasing. This is the concentration of holes. It is less than the concentration of immobile acceptor ions. And this is concentration of electrons. In this range, there are very few electrons. That's why the concentration of electron is far less than concentration of Na. Initially, when there was no positive potential, this P was equal to Na, indicating p-type substrate. When we refer this equation for this region, this term seems to be dominating because Vs is positive, Q is positive. But there is a fraction N naught divided by P naught. N naught is far less than P naught. In the depletion region, the concentration of electrons is far less than concentration of holes. That's why this term will not be dominating. In that case, the Qs will vary as per square root of surface potential in this range. And for this section where surface potential is greater than Vf but less than 2 times Vf, this is called weak inversion. Here, electrons start assembling in the channel near the interface and its population start increasing. You see, concentration of electron is now more than the concentration of holes over here. This is called weak inversion, start of making inversion layer. When in the fifth reason, when Vs is far greater than 2 Vf, this is called strong inversion. And in this reason, this term is dominating because N naught is greater than P naught. That's why the whole concentration of electrons and electronic charge will increase exponentially with higher values of surface potential in the positive direction. This is the exponential rise. So this is the overall picture of variation of surface charge per unit area with respect to different values of surface potential. And this curve has a very peculiar shape across these 5 regions.